let me now state our main results. So the theorem A is the following. So let X be an n-dimensional complete asymptotically Euclidean spin manifold of non-negative scalar curvature and compact boundary. And suppose again that X0 and X1 are codimension 0 submanifolds with boundary, such that these inclusions are satisfied. And moreover, suppose that X0 contains all asymptotically Euclidean ends of X. And moreover, we assume that the scalar curvature is greater or equal than K times n times n minus 1. So clearly, this is just a normalization constant to make the inequalities look a little bit nicer on X1 minus X0 for some positive constant kappa. Moreover, let D be the distance between the boundary of X0 and the boundary of X1, and L be the distance between the boundary of X1 and the boundary of X. Now define the number psi depending on D and L, using the following formula. Okay, so in other words, is this expression if D is more than this number and L is more than this number, or infinity otherwise. Lambda of D is, well, this expression. Now, if the mean curvature of the boundary of X satisfies the following inequality, so it's greater than minus this number psi, then the ADM mass of each end is strictly positive. Here is the picture. This region is X0, and this region is X1. And now we want an inequality that involves, well, the distance D between the boundary of X0 and the boundary of X1, and the distance L between the boundary of X1 and the boundary of X. And our curvature assumptions are that the scalar curvature is greater or equal than a certain constant kappa 0 that I will normalize as kappa times n times n minus 1, and that the scalar curvature is non-negative everywhere. Notice that this theorem can be thought of as a non-stretchability principle. So in other words, once we have information on this region of the manifold, then we know that the metric cannot be extended more than a certain distance L if we want to keep the scalar curvature non-negative. We now state our second main theorem. So this is a localized version of the positive mass theorem, saying that, well, suppose that E is a n-dimensional asymptotically Euclidean end, such that the ADM mass is negative. Then there exists a constant depending only on the geometry of the asymptotically Euclidean end E, such that the following holds. So if M is any n-dimensional Riemannian manifold without boundary that contains EG as an open subset, and suppose that U is a open neighborhood of radius R around E in M, then at least one of the following conditions must be violated. So that the closure of U is metrically complete. The second condition is that the scalar curvature is non-negative on U. And the condition number 3 is that U is spin. The intuition is that when the mass of an asymptotically Euclidean and E is negative, then the hypothesis of the positive mass theorem must be violated in the R neighborhood around E, where R is a constant that only depends on the geometry of the asymptotically Euclidean end, and not on the geometry of the entire ambient manifold M. Now, in the case when E is a asymptotically Euclidean end in a complete Riemannian spin manifold M, this theorem yields the positive mass conjecture with arbitrary ends. So in other words, as a corollary, we obtain a theorem that was proved by Bartonik and Kruschel in 2005. So let M be a complete connected and dimensional Riemannian spin manifold without boundary, such that the scalar curvature is non-negative, and suppose that E is an asymptotically Euclidean end. Then the ADM mass must be non-negative, and moreover, if the ADM mass is 0, then M must be flat and therefore isometric to the Euclidean space. Of course, for the rigidity part, we have a separated argument. As already observed, we expect that theorem A has a counterpart for the Geroch conjecture, and in particular, we can prove the following theorem. So suppose that X is an n-dimensional open spin manifold, and suppose that G is a Riemannian metric of non-negative scalar curvature on the connected sum of X with the n torus. Now suppose that X0 and X1 are codimension zero submanifolds with boundary, such that the following inequalities are satisfied. And moreover, we assume that X0 contains the torus minus a disk, where again, I'm identifying this with a subset of the connected sum. Moreover, we assume that the scalar curvature is greater or equal than our normalized constant kappa n times n minus 1 on X1 minus X0 for some positive constant kappa. Then first, the distance between the boundary of X0 and the boundary of X1 must be smaller than pi over n square root of k. Moreover, if U is a neighborhood of X1 with L, then L must be smaller than 1 over lambda d, where lambda of d is defined by this expression.